Internet videos speak to several kinds of ternary analysis, most often metal phase analysis. But a few address fire hazard analysis also, and that is something I have been promoting for several decades. Hopefully this video will complement the resources available today on the net. Ternary diagrams and related materials are a very powerful, but very much hated safety tool. Frankly, I hate them myself. They are complicated, confusing, easy to misread, but their use is often unavoidable, and they are better than the alternatives. However, much of their onus can be greatly mitigated with computer algorithms. This first video focuses on my computer efforts, which date to the 1980s and include the coding of a demonstration computer algorithm, which is the subject of this video, for fundamental ternary analysis. Later videos may go further. For the decade of the 2000s, a compiled Visual Basic 3.0 16-bit algorithm was on a personal website, and I made approaches to industry standards groups to adopt it. Concentrating most as a charter member and past chairman on ASTM Committee G4, a standards committee dealing with oxidant fire risks, but also approaching ASTM Committee E27 on hazard potential of chemicals, which publishes both a fire limit test standard and a computer software program titled Cheetah for predicting explosion risks, and finally NFPA 53, dealing with oxygen-enriched fires specifically affecting consumers. To date, there has not been a shred of interest among any of these experts, a disappointment that does not, in my humble opinion, reflect well on all these committees' public service missions. Indeed, aversion to using ternary diagrams has been voiced most loudly as the basis for opposition. Hence, I am launching this tutorial addressing plain vanilla fire limit analysis and hope to follow it up with supporting materials for the foundations of ternary analysis and on generic approaches and more advanced methods in hopes of drumming up some interest somewhere. This and any later planned video is summarized, including a discussion of my public domain computer program, in a small public domain book that I hope to get Amazon to run on-demand copies of, but have not been successful at that yet. More work to do there. The algorithm I will demonstrate in this video began life in the 1980s as a Microsoft 19K basic program, for those who remember that far back, to convert mixture concentrations between formats. When 16-bit Visual Basic 1.0 came out in 1991, it was an obvious tool to build in a lot more power. This led to a program in later Visual Basic 3.0 in about 1997 that I called FLLAME, Fire Limits for Linearly Afflicted Minds Everywhere, with 2 L's, hoping to have a unique name that would allow easy discovery in Google searches. Unfortunately, a rock band with this same name got the first several pages every time. By the later 90s, a rather nice algorithm for treating and learning the most basic oxidant, fuel, and diluent systems and their mixtures was produced, and a small number of co-workers found it useful. Upon retirement, I sought and was given release to pursue and promote the algorithm, and I pitched further development and standardization to everyone I knew of, and made the compiled VB3 program available on the internet for nearly a decade, only to encounter the extreme aversion to use of the diagram. The following 20 years found no diminution of the aversion for this powerful analysis. Today's 64-bit PCs are common, and many, maybe all, do not run 16-bit software. As a result, in order to demonstrate the concept here, the old VB 3.0 code was partially upgraded to VB 4.0 32-bit software, still circa 1990s, to demonstrate here in compatibility mode on a 64-bit machine. Although I consider it a valuable analysis and learning tool, indeed, much more power can be incorporated by way of additional resources and additional types of analysis and additional dimensions of analysis. The internet goes everywhere, and so this last-ditch effort archives my past work and will seek a route outside these standards groups to promote progress. Perhaps an open source community can form. However, if the world really wants nothing to do with this material, so be it. It can wither out there on the net. But for now, we will examine typical data in the literature, data like the following. Let's examine the most typical data types found in the literature. This is a right triangular plot for the flammability of methane, modified from Zabatakis' famous Bureau of Mines 627, page 10, but with some material removed. This is an equilateral ternary plot, also from Zabatakis, page 9, and also modified somewhat. Look at the triangular part to the right of the air line. Here is that triangular region, again plotted on Zabatakis, page 28, but in rectangular format and with data for 5 additional diluent gases shown for methyl bromide, carbon tet, carbon dioxide, water vapor, and helium. These 5 gases cause this to be a ternary plot of quaternary mixtures. Only the curve marked nitrogen, N2, is for a true ternary mixture. However, for all these quaternary mixtures, the ratio of oxygen to nitrogen is constant. This shows how the quaternary data look when they're added to the ternary data for the full methane, oxygen, nitrogen system. The various plotting styles for all these graphs are equivalent and can be cross-converted into each other. And why one graph method was chosen over the others is open to speculation. There are also numerous theoretical methods used to obtain data for risk analysis, including theoretical estimates of the thresholds of combustion, the fire limits, based upon heat balance, heat capacities, kinetics, minimization of Gibbs free energy, and even rough geometrical estimates are used. But there are also many pitfalls in doing that. In many cases, experimental data are the gold standard for analysis. A typical method of ternary analysis, which I have seen used a number of times, and an example of which has been and may still be on the net, constructs a coarse ternary diagram, and I have seen this method used in practice in industry and do not disparage it. In this coarse approach, the pure constituents are at the apexes of the ternary graph. If published in the literature, one then plots the upper and lower fire limits on the fuel-oxygen or fuel-air axis as shown here. Then one plots theoretical stoichiometric compositions and plots the minimum oxygen for combustion, also if published, and assumes it occurs at the stoichiometric condition. This is yet another approximation, but min oxygen is typically close to stoichiometric mixture levels. Then one draws in a triangular fire zone estimate by connecting the min oxygen point with both the upper and lower fire limit points. I repeat, these are approximations, but often good ones. Here we see actual experimental data from Zabatakis that you have seen before for methane. Also shown is how the course construction looks, and the fit is really pretty good. Yes, you would need to be careful about safety factors, but this is usable. However, there will always be exceptional, albeit rare cases where this approach is not this good, as is the case for when multiple modes of combustion obtain, as for example with cool flames. Here we have the ternary for ethyl ether with oxygen and helium, which is plotted from Venerable Coward and Jones, Bureau of Mines, publication 503, page 90. It apparently can burn in one scenario with a robust fire, the lower area, but in the right circumstances with a more timid fire, called a cool flame, which is the upper area. Green squares indicate the published upper and lower fire limits. Although the min oxygen data point is not published, we can take it as being near the nose of the curve, and the dotted lines show how a constructed fire limit diagram would look that might be less than ideal for practical use. If we wanted to focus on the intense combustion region, the constructed triangle for that region would be an even less good fit. And if we were focusing on just the ethyl ether air helium region, the constructed triangle would be a much less good fit. You can find video that duplicates my experiences in industry in which even those who are forced to do ternary analysis cobble together a course diagram like this for the UFL, LFL, and MinO2 data, and then struggle through estimates of various properties and must then add a generous safety factor to any determinations they make. And this is why I sought a better mousetrap all those years ago. At this point, it would be prudent to be, and you should be utterly wary about doing ternary analysis. Really smart people have at times been daunted by it. Ideally, consensus understandings of these data for gases would be much preferably scanned from the literature or cataloged as JPEG computer files, and then imported into a reader algorithm. Indeed, numerous reader algorithms in this and other fields would serve the world well, and yet sadly, there does not appear to be any, to the writer's admittedly limited knowledge. But let's look at just one. My own FLLAME 1997 effort, which I've recently partially upgraded to Visual Basic 4.0. This is the rectangular format starting point for FLLAME, a format you saw earlier. It is preceded by a series of CYA screens so that the as-is and use-at-your-own-risk nature of this effort is made clear. Notice the graphical area presented has an abscissa for 100% to 0% oxidant left to right. The ordinate is 0 to 100% fuel, bottom to top. And there is a default vertical line where the relative composition is at a constant 21% oxidant, 79% diluent point, which is the composition of oxygen in air, and this is regardless of the fuel constituent in it. On the right, starting from the top, is a menu to access cataloged fire limit data from the Bureau of Mines for several materials. Below that, 3 command buttons to select standard, rectangular, or ternary formats, or can wipe the plot clean of analysis metrics. Below that are morph slide controls and a slide control to truncate the left axis of the plot. Below that are option selectors to plot any of a range of metrics that might be needed. Below that is a region for the program to report the current values for the location of the pointer and active metric. Along the top is a bunch of operations that can be executed to print or teach or set up specific applications or create additional data plots to import. Not all of them still work in this VB4 version, but we will use the option buttons to designate mobile metrics. Let's start by just showing how it works and if I got it right. And note how it takes much of the nightmare out of ternary analysis. First, I import data for 3 interesting materials. Here's data for methane, carbon monoxide, and hydrogen. And this is how these data look plotted in standard rectangular format with a limited number of straight-line connected data points from Bureau of Mines literature. Let's focus on just hydrogen. Here is what hydrogen looks like in ternary format. This format straightens out many data sets into a near triangle. These limits here are well behaved, are very triangular, for specific thermodynamic reasons that time will not allow to be examined here. But we have seen there are also some that are not so well behaved. Now we go back to standard. We can zoom with a slide of the zoom control to exhibit only the standard style data for mixtures with air, or zoom it back. We can convert the data in air into ternary format with a second click, and now go back. The morph control allows us to see how these data appear in transition. Many unconventional plots that do not appear in any literature are also possible, yet all are also valid. If we want to know what ISO composition curves look like through any point, we can click on their respective option buttons for constant fuel to oxidant ratio, fuel to diluent ratio, oxidant to diluent ratio, oxidant, diluent, or fuel, fuel to added oxidant ratio, fuel to added diluent ratio, reference oxidant diluent gas mixture, in this case air, added oxidant or added diluent to the reference mixture. While all these might be intuitive if you are a savant, here is what these metrics look like through, let's say, this point here. And here is what their ternary analogs look like. And the percentages for selected metrics among them at that bullseye are listed in the report box. Note that if we watch the oxidant to oxidant plus diluent ratio report and click at points along the reference air curve, it tells us that the oxidant to oxidant plus diluent ratio there is about 21%. Did you know that? Now we examine some specific analyses. Here is the curve for methane by itself in the dreaded ternary format. First, we go to the Options button and select a methane ISO composition mobile guideline. Then return and elect to freeze it when clicked. This red fuel metric exhibits all possible combinations of the 3 gases that contain the same concentration of methane. We then move the pointer in the increasing fuel direction to first contact with the fire region and click to freeze it. We see that in the ternary mixture, the minimum methane, the lower fire limit, the LFL, regardless of the other two relative percentages for sustained combustion, is as reported to the right, about 5%. We could now print this graphic out for a project file. Note that the ternary limit is the same as occurs for binary limits on the left axis as well. This is not always the case. Now we can wipe and move the metric up until it hits the last point where it contacts any part of the flammable region and freeze the metric again. This is the three-component upper fire limit, the UFL, and we could print this out and save it in a project file. This maximum, the UFL, is about 61%, consistent with published data. And again, the binary case matches the ternary case, and again, this is not always the case. We now wipe and go back to Options, switch to the Oxidant Metric Mobile Guideline, return, and choose the option to freeze it, and repeat the procedure, this time with a blue metric, and we see that the minimum oxygen for combustion is about 12%, which is also close to published values. Wiping and returning, we find the maximum is in the neighborhood of 95%, and this value is not typically tabulated. If we now wipe and go back to the Options button and switch to a diluent, in this case nitrogen mobile guideline, and come back to choose the option to freeze it, we then can use a green metric to see combustion is possible even in the absence of diluent. The min diluent is 0. Wiping and returning, we find the maximum diluent is about 82%, and this is again not typically tabulated. Let us now look at binary feedstocks. In many cases, one is looking to mix materials. For example, here we see a vessel that contains a gas or gas mixture, let's say methane. Perhaps we want to purge it out or add another gas to it, let's say oxygen or nitrogen, or a mixture of oxygen and nitrogen, perhaps the most famous mixture, air. When you mix two gases, all of the intermediate mixtures from the one pure gas to the other pure gas can form. But you should really try not to form mixtures that can burn, because they can, and at times they do catch fire or even explode. Remember that on a ternary diagram, the straight line that connects any 2 points represents all possible intermediate mixtures of the endpoint gases, whether pure or mixtures themselves. Here is methane again, and on it notice 3 straight lines. The left oxygen fuel axis, the right nitrogen fuel axis, and the broken reference air fuel mixture line. The left axis is between the pure oxygen and pure methane apexes, and the connecting line passes through the fire region. Hence, one might not want to purge the methane with pure oxygen to avoid forming any of them. The broken line is between the pure air point and the pure methane point, and also passes through the fire region. Hence, is also not a good purge gas prospect. The right axis is between the pure nitrogen and pure methane points, and the connecting line does not pass through the fire region, so nitrogen is a potentially safe purging fluid. Now I'm going to select to freeze 3 constant ratio binary mixture metrics: the constant fuel to diluent metric, the oxidant to diluent metric, and the fuel to added diluent metric. And I'm going to carefully freeze 3 binary mixture lines that almost touch the fire region here. Then undo the options for the rest of the analysis. If we wanted to safely purge this vessel to air or oxygen contents, we might just want to follow one of the new possible routes shown here, that, with a prudent safety factor applied, does not pass through the fire region where a fire or explosion are possible. Assuming the vessel contents mix well, the most conservative route, which is probably the slowest and most expensive, is to purge the vessel with nitrogen until the methane concentration in the vessel is 0. Then we can add oxygen or air to get to the final goal of air or oxygen. However, we could also add nitrogen to this point where the vessel contains about 11.8% methane with nitrogen, then purge air to get to the air point more quickly and with less purge gas expense. Then purge to oxygen if desired. However, if oxygen is the final destination, one could interrupt the air purge at this point of about 5.5% methane, 11.8% oxygen, and 82.8% nitrogen, and start the oxygen purge directly. These are probably the quickest and cheapest routes. One could also purge the pure fuel with nitrogen to this point of about 5.7% methane in nitrogen, then switch to a pure oxygen purge if oxygen were the final destination. And finally, I note that this point here is the 12.2% published min oxygen and nitrogen combustion limit. If you had a source or could blend 12.2% oxygen and nitrogen, you could purge the vessel to this point just off the nose of the fire region, and then elect any of 3 routes. Switch to pure oxygen to the oxygen point, switch to air to pure air, and then on to oxygen if desired, or purge all the way to pure gas, 12.2% oxygen and nitrogen, and then on to the air or oxygen. Of course, with each case, one must decide just how closely one can get to the fire region to prevent glitches from creating a hazardous trespass. Similar approaches are used to go between any points on the diagram, and in a more generic analysis that may not be for fuel oxidant diluent, but might be for, say, fuel oxidant oxidant, or fuel fuel oxidant, or any other combination. And of course, then there are higher order cases, like the quaternary cases of fuel fuel oxidant diluent, or fuel oxidant oxidant diluent, which are reserved for possible later analysis. And Einstein thought space-time was difficult to do. There's an old saying, not used much anymore: build a better mousetrap and the world will be the path to your door, perhaps wrongfully implying you will get rich. Not so today, for this is a better mousetrap, and so far the world does not give a damn. We surely do live in interesting times. There are 2 more potential videos I have alluded to that I could and may prepare. One on the foundations of these analyses, and one on making them generic and increasing their power. However, the upgrading of this software to 32-bit status was not so onerous, So just to be ornery myself, I may increase the screen resolution of the Analyst from its present 1992 style 640 by 480 pixels to at least 1028 by 720, or a much more common screen resolution in use now, since that will provide a more precise result and much more screen content. But nature sides with the hidden flaw, and there is always the chance there will come an incident that will reprogram the thinking of today's experts and encourage more receptivity to the use of this tool or a next-gen alternative or even a derivative. Time will tell, I guess. The end.